So yeah, thanks for everybody for being here. It's been a great week so far. I'm looking forward to tomorrow. It'll be a nice, dense session, and hopefully I can not go over time so everybody can go home and get some rest. Today, yeah, I'll be talking about sort of some recent work with Eric Bouveau and Philippe Malbos, which sort of combines two of the themes of the week. So on the one hand, persistent homology, and on the other hand, concurrency and directed spaces. So now I need to click again. Sorry? No, I am. Don't worry. It's just the way that the screens are set up. Okay. Yeah, sorry. But it's good. You're on the ball. That's good. So yeah, so first I'll briefly talk about persistent homology. I think we've already heard the story many times. Then I'll talk about directed spaces and this invariant called natural homology. And then at the end, we'll see how we can recover natural homology using uni-dimensional persistence. Okay. So I'm going to take this my very naive approach to persistent homology, which is the sort of you've got a point cloud into maybe large Rn, and we want to obtain some kind of spatial information about this data set. And this can be very hard because of noise, first of all, in the data, and also because we have difficulty understanding spaces or visualizing them when n is greater than 3. So what we do is we sort of start with our points and we expand them in some way, create a simplicial complex that grows over time. There's sort of an evolution. We calculate the homologies of these simplicial complexes, and then we get some kind of nice, clean information in the form of a barcode, which tells us about the large scale and small scale topological features of this point cloud. So we have this idea of spatial evolution, right? A sequence of simplicial complexes. And this equivalently, we can think of it as a functor from the category, the poset of natural numbers viewed as a category into the category of simplicial complexes with inclusions. Now we apply homology at each one of these simplicial complexes, and we obtain a sequence of F vector spaces, if that's the kind of homology we're doing, which it is in this talk. And then we can again just view this as the composite functor of the one that we had in the beginning, this K dot, and the K homology. So this gives us this set of linear maps, basically, and these are the things that are going to be important in persistent homology on some level, because they are telling us how the generators evolve throughout this filtration, right? So anytime we have P less than Q, we have this unique linear map between the P, the KP and the KQ. And this gives us a notion of life and or birth and death of a generator. So we'll say that a generator is born at P if it's not in the span. Yeah, if it's not in the span of the previous map, right? And we'll say that it dies if it's in the kernel of the one that's just about to come. Yeah. So here we have a picture of a generator that's born at n and dies at n plus 1. Again, this is stuff that all of us know from all of these great tutorials we've seen this week. Now we get, oh, somebody's calling me. Now we get a barcode, right? Which is just a way of encoding the lifespans of all of these generators. Yeah. So these are just pairs of natural numbers, which represent each of which represent a generator, which is born at n and dies at n, right? So here's a very toy example where we've got a very easy, simple sequence of simplicial complexes. And we see first that we have one connected component over here. At level 1, we have the birth of another connected component. It dies because we connect them. A third one appears because we've added this point C. And that one persists until infinity if we extend this finite sequence by just the identity every time. And what's important here is that we're tracking the way that generators are identified as we move through the filtration, right? And again, I'm just pointing all this stuff out to make analogies later on when we see what persistence looks like in the case of directed spaces, because the interpretations will be slightly different. Okay, so now we get to directed spaces and natural homology. I guess we've already seen directed spaces this week, but just to again be sure that we're all on the same page, I'll recall that a directed space is just a pair where we have a topological space X and some set of continuous maps from the interval into X. Okay, and these we call them dipaths or directed paths. And these should be, first of all, contain all the constant paths. We should be closed under concatenation because we want to be able to compose things. And we should have all the reparameterizations of maps because, and I'll make this more clear later, we really don't care how quickly we go through these maps. We just care about which points they pass through, right? Because, yeah, we'll get to that in a minute. So this is a directed space. It's some kind of richer version of an internal category in the category of topological spaces, right? This is kind of what this encodes. So, for example, partially ordered spaces are naturally equipped with the structure of directed space. We just take the increasing paths. Directed graphs could be seen as directed spaces. Precubical sets we've heard about this week as well. And here's a nice geometric realization of a precubical set called the matchbox. I believe Fahrenberg's matchbox actually. Uli's not here. And it's just an empty cube where we've taken out the lower face. Okay. And here we have 6 maximal directed paths, which, yeah, I've listed here because we're going to use this as a running example throughout the talk. Okay, so directed paths, directed spaces, this is all fine. But really what these are maybe somewhat mainly used for, let's say, are for giving us a semantics of concurrent programs, okay? And in this view, the executions of the concurrent program correspond to the different directed paths through the space. So we saw, for example, in Uli's first talk that they're sort of tackling the problem of scheduling and interleaving of paths. And so really we only care about where the path goes and not really how fast we run through it, yeah? So for this reason, we will quotient out our dipaths by reparameterization, so we're only really looking at the image of the path, yeah? And we call these things traces. So the equivalence class is under this quotient of reparameterization. We call these things traces, and these will be kind of the objects of our study, okay? We want to understand what kind of traces we have in our space, how they're equivalent. This is kind of what we want to characterize using our natural homology invariant. So in order to define this natural homology, we're going to have to define a few categories. So like I said, this directed space is sort of encoding a category, and it is sort of this category. It's called the trace category. The objects of this category are the points of the underlying space, and the arrows are just traces. So this is sort of the boiled down information. We've forgotten sort of about the topology. We're just looking at the way that points in the space are connected by traces. And we're going to look at the factorization category of this trace category, which is called f p of x. And this sort of, since we're studying the traces, we go up a level and we look at the category in which the traces are now objects, and the arrows between traces are extensions. So an extension is a pair of traces, u and v. And we'll say that this pair goes from alpha to beta if beta is equal to u concatenated with alpha concatenated with v. Yeah, so it's just a sort of subpath relation, right? This is also called the twisted arrow category, as we saw on the first day. It's a nice, these are called, this factorization category is a nice way of dealing with homology and categories, let's say, I think first in sort of, I think first used by maybe sort of Gibladze and Quillen and people like this. So natural homology is called natural homology due to the use of functors on the factorization category being a sort of natural generalization of modules on a category, okay? And so functors going from the factorization category into the category of abelian groups or vector spaces or something like this are called natural systems. So this is where this terminology comes from. It's not because we're claiming that it's the natural homology. So now we're getting to the definition of this thing. But first we need to get some kind of spaces that we can calculate some homology, right? And since our objects are the traces, well, we're going to look at what kind of space we can associate to a trace. So if I take a trace alpha, I can just look at all of the parallel traces, yeah? So all the things that start at the same point, end at the same point, and topologize it with compact open topology, for example. But there are also very nice ways of calculating these trace spaces as simplicial complexes in nice cases, as Christoph knows very well. For example, with pre-cubical sets, we can calculate some simplicial complexes given any trace. Yeah. So for example, back to the matchbox, if we look at all of the traces between these two blue points, so we have two of them. Zeta 2, I say that just because we've taken 2 steps along zeta, and alpha 2. And of course, we've taken out the lower face of this box, yeah? So these things are not connected in the simplicial complex. However, if we look at the side face between these 2 points, see that epsilon 2 and delta 2 are the only 2 paths that we have. However, since this face is there, they're actually connected in the associated simplicial complex, yeah? So now that we have a way of associating spaces to traces, we can go from this factorization category of the trace category. We can obtain some simplicial complexes or topological spaces, and then we can apply the homology functor, okay? And this composition is called the kth natural homology, all right? I think actually, technically there should be a dimension shift somewhere, but it's not so important. The point is that, first of all, this is a very large invariant, okay? This factorization category of the trace category is quite big in general. So it's a kind of it's a nice invariant, but it's hard to calculate, okay? Also, we see that we have some functor, which is going from some category into simplicial complexes, and then we're composing with homology. So we have a sort of similar picture to the one that we had at the beginning when we were talking about persistence. And this is kind of the fundamental observation of this work, is just that this is actually a persistence object in the sort of general sense. And that's what I'm going to make clear now in this third and final part of the talk. So I have a lot of time now, that's great. Okay, so before, when we were talking about persistence, we were talking about uni-dimensional persistence. So just functors from n into vec f, yeah? But we can talk about persistence in a more general setting, almost too general in a way. And this is just if we have some category, that'll be the category of the sort of type of our persistent objects, and a poset, then we can talk about p persistent objects in C. And these are just functors that go from P into C. Now, in sort of well-behaved directed spaces, the factorization category of the trace category actually has the structure of a poset. So this idea of extension, this subpath relation, actually is an order relation, okay? So we naturally just have a poset, and so by just changing our notation a little bit to say that we have a poset, we have a persistence object now. Instead of having this big, scary invariant, now it looks like a persistence thing, so we can maybe hope to calculate it in a nice way. But it's not a, let's say that it's, in general, it's a very complicated post set. We don't really know how to calculate persistence over it very easily. Maybe if we just had sort of a n to the d for some d, it would be a little bit easier. But the point is that it's not going to lend itself to calculation very easily, right? But the objects of study, these traces, these are one-dimensional objects, right? And actually, these give rise to uni-dimensional persistences, okay? So how does this work? We take a trace, and we actually take maybe a representative of this trace, let's say that we parameterize it by constant speed or something like this. We subdivide the interval into some, however we want. Maybe we have some nice way of doing that. Maybe we just split it up according to some given epsilon. But we take a subdivision of the interval, and then we can just restrict this representative of the trace to the interval 0 to tk. Yeah, and then each time we move to the next tk plus 1, tk plus 2, we're actually just extending our die path a little bit each time. Yeah. So this gives us a chain in the post set of traces. Yeah. And now, if we take the associated simplicial complexes, we get a filtration of simplicial complexes, and then we can apply homology and get a persistence vector space. So now, we take a trace. This gives us a chain in the trace post set, and then we get a barcode by applying our uni-dimensional persistence algorithm. Yeah. So each of our traces gives us a barcode. Again, interpreting this well is not completely clear yet. I guess when you see the birth of a generator, this means that you've had some kind of branching which has come together, and there's a hole between them, right? Moreover, I guess especially in lower dimensions, you won't have generators that die ever. This will only happen in higher dimensional settings, or for higher homology groups. But in any case, we have now something we can calculate, right? So let's go back to the matchbox and look what kind of barcode we get for this kind of persistence, uni-dimensional persistence along the trace alpha. So alpha 0 is just stationary at the initial point of the matchbox. Then we extend alpha 1, we still just see one directed path, right? But as soon as we extend one more step to alpha 2, we now suddenly have another trace in the trace space associated to alpha 2, namely zeta 2, as we saw in a previous slide. Also, as we saw in a previous slide, in this simplicial complex, alpha 2 and zeta 2 are not connected because we don't have the lower face of the cube. When we extend to the terminal point, now we suddenly see all of those maximal die paths or maximal traces that we had, and moreover, they're all homotopic to each other because we can sort of slide along the top faces and connect them all. So now we just have one connected component again. So we get this barcode which shows alpha persisting for 2 steps. Then we have the appearance of, we have the birth of zeta at 2, the death of zeta at 3, and then just this one connected component that persists for however long we want to consider this filtration to last for. So this is how we can go from a directed space and one trace to a uni-dimensional persistence and obtain a barcode which sort of tells us how the holes in the trace space are evolving as we move along the trace alpha. Okay? So now we want to somehow use all of this information about persistence along chains or along maximal traces to recover natural homology somehow. And we're basically going to do this in a theoretic way for now. using colimits. So basically, we're going to say that, well, we have all these chains in our poset, and we know that if we paste together all of the chains in the poset, then we obtain the poset, right? So this is what I'm going to go into for a minute now, because we actually have ways of doing this that are maybe a little bit smarter than just taking all the chains. But anyway, we all know what a chain is. It's just a totally ordered subposet, right? Now, we can look at this category of chains in a given poset P. So the objects are just the chains, and the morphisms are inclusions of chains. Just the sub diagram in the category of posets given by the chains of P. We have an inclusion functor DEP, which sends the chains into the category of posets, and its colimit in posets in the category of posets is exactly isomorphic to P, right? However, we could maybe want to reduce this information and not use all of the chains, so that we're kind of being a bit more intelligent about how we calculate. So we could look at pullbacks, for example, right? If we take two chains, we can take their pullback. Basically, this corresponds to the induced subposet of the intersection of P1 and P2. But the problem is that it's not a chain. I mean, yeah, the pullback is not a chain really in general, right? For example, if we have this diamond shape, we have two maximal chains. If we do their pullback, we get just we get a discrete poset on 2 points. So this is not great. I mean, again, we can take all of the chains, but really what we want to do is reduce the number of chains that we have to calculate our persistent homology along, right? So we'd like the maximal chains, which naturally correspond to maximal traces in the directed space. But doing this pullback is maybe not the best thing, right? So instead, what we can do is a quasi-pullback. So this is just sort of only taking those intersections that are maximal chains, all right? So a quasi-pullback of C1 and C2, it's like a pullback diagram, except for that it's not unique, okay? So if we complete the maximal chains in P by quasi-pullback, we get a category that I call quasi-maximal chain category of P. And of course, if we just do the pullbacks, we'll still get a nice colimit. But we will also get this colimit, of course, if we use the quasi-pullbacks. So now we have a smaller diagram of chains, which gives us the desired colimit. And in which we're only considering chains, so we're only doing uni-dimensional persistence. Okay, now that we have established some results about doing colimits of subdiagrams of some poset, we want to see that this carries over to functors on posets into some category, right? So for this, we introduce another category. So this is the category that looks at all of the functors from posets into some fixed category C. So the objects are just functors F from some poset P into this fixed category C. And the morphisms are pairs of poset morphisms and natural transformations between this F on the left and the composition of phi and G. And we call this the category of P persistent C objects, and we denote it by this pers of C. Okay, so now we have some kind of result which tells us how we can, using a colimit of posets, just recover a colimit of persistence objects. Yeah. So the setup is that we have a persistence object H, which goes from some poset into C. We have a diagram D, which is giving P as a colimit. And as long as C is a co-complete category, then H is actually the colimit of some functor, which is just given by the restriction of H to each of these subposets of P. Yeah. So it's really just, if I can glue together P out of some subposets, and I have a diagram from P into C, then I can also glue together the diagram by restriction, right? It's nothing complicated is going on here. But the nice thing is that in the case of natural homology, well, we've got this poset P of x, this poset of traces, which is the colimit of all of these different functors that we talked about before. Most notably, I guess, this quasi-maximal chain category of P. And the category of F vector spaces is co-complete. So we can apply this, this result we had on the previous slide and recover HK of x as the colimit along chains in the trace poset. And actually, it suffices to just calculate the unidimensional persistence along each maximal trace. Then, of course, we still can just restrict and have it on all the quasi-pullbacks. And so we just need to calculate the unidimensional persistences along each of the maximal traces in order to recover the whole diagram. Okay? So this is kind of the nice initial result, let's say, that's linking natural homology to persistent homology. Now we go back to the matchbox one more time. Here up at the top is the Hasse diagram of the trace poset of the matchbox. Okay, so I remind you that here we have all of our 6 maximal paths, which are the 6 paths at the top, and we have some different extensions that connect in different ways. I put red circles to indicate which paths share the same endpoints. And if we identify endpoints, that is basically if we take the colimit by the functor that I was talking about, we will get the natural homology of the matchbox. Okay. So the main thing is by just observing that in nice directed spaces, we naturally are working with a poset. We can establish this link between natural homology and persistent homology. And just recapping that we really, there's also this nice, I guess, just moral similarity that in concurrency, we're interested in these one-dimensional objects, and using persistence, we have really nice ways of efficiently calculating one-dimensional persistence, right? And we can recover using a colimit, the whole diagram using these unidimensional things. So future work or outlooks or things that would be nice to discuss with you guys for the remainder of the conference and in the future, I hope, would be to actually implement this somehow and find better ways of doing it for calculating these, the whole diagram or sub-diagrams, interpreting really what we can then know about the space from these things, exactly what it means, right? Because as I said in the beginning, we have a very clear idea of what it means in the case of persistent homology to analyze some point cloud or something like this. Here, it's less clear. Also, there's a distinction between what we're doing, right? Because if we want to understand the entire directed space, the sort of total trace space, the maximal trace space, this is the object that we really want to understand. But it's sort of at the end of our filtration. Yeah, it's not at the beginning. Whereas usually in persistence, the thing that we're starting with is the thing that we want to understand, and then we sort of let it grow. Right here, it's like we start with something very trivial, and then we see how it's evolving. Anyway, exploring these links would be really great. Also, of course, all of these amazing advances in multidimensional persistence that we've heard about, notably in Magnus's talk yesterday, it'd be very interesting to see. Sort of in pre-cubical complexes, we have a very natural sort of grid shape. And since each time there's one unique extension, usually of dimension 1, we would naturally get functors from nk into vec f, and understanding the links between natural homology and this multi-parameter persistence would be great. And moreover, we have some nice structural properties of these natural systems, of which natural homology is an example, such as composition pairing, which don't naturally appear in persistent homology, but which maybe give us some nice information we could sort of also transport things in the other direction, perhaps, right? I think that's all I have to say. So thanks for your attention, and
are there any questions?
First of all, we start by looking at path in a way of being indexed by dimensional numbers, so some dimensional numbers. Since it's a factorization category that you take point of starting, I think it's more natural to take intervals in dimensional numbers at point of departure, which means you start from the path from one point to the same point, and extend to both sides.
Yeah.
So that's a more natural way to, to get the factorization idea into the picture.
Yeah.
And the second comment is that I think it would be interesting to consider the component categories that also have been discussed by the factorization or factorization and to look at it in this framework, because you can right away reduce the number of chains that you
Exactly.
before starting the whole endeavor.
Yeah.
And then, of course, the last comment is calculating these homologies and so on. That's not for that's a hard thing to do.
Yeah.
And in principle, there are tools for that, but I'm able to say it's in principle.
Yeah, well, it's, definitely in principle for sure. Yeah, I think that the outset was to try to begin to move towards being able to calculate natural homology, but I agree that it's very far away. And also, yeah, it would be great to talk more about the component category. Hopefully my spring is less crazy than my summer, and I can finally come to a goal and talk about it. So, great.
Any more questions or comments?
Just a question regarding the structure of
Mhm.
Going to products, is there how does it behave with respect to products?
Like products of directed spaces.
Yeah.
I'm not sure. I think it works quite well. I think that it satisfies almost all of the nice homology axioms except for excision.
And products is the solution of product of this diagram.
Yeah.
It's mostly infinite formula for each component.
Any more questions? I would like to ask, what's the level of generality? Assume something about your directed spaces? Or
So for now, what I'm completely sure of is that if you're loop-free space, which is not Hausdorff, then you have a poset for your trace category, for the factorization category for trace category. There might be some larger class of spaces for which it's true, but I mean, basically, you need, first of all, that that a trace is sort of characterized by its image. If you have a loop, suddenly you can't have any kind of nice poset property. But I think definitely precubical complexes, definitely Hausdorff and loop-free. These are the assumptions that I have for now.
Thank you. Any more questions? If not, let's thank the speaker again.